Hey everyone, how are you guys doing all these 2 weeks? I hope you had a great time and now we are all ready and set to start our lab where we left a couple of weeks back. And today I'm going to talk about pulmonary function tests. Now, before I start this presentation, I just want you to have an overview of what we are going to talk about today. We want to know why we are going to talk about PFT, and then I'll give you a very quick overview about the mechanics of breathing. And there are a few definitions which I want you to know before we dive into the classical pulmonary function tests. We'll discuss the technique of spirometry very briefly, and the main chunk of our discussion today is about the lung volume and capacities, the static component, and the dynamic component. And then we are going to use these components to interpret the obstructive and the restrictive diseases. And at the end, I'll just walk you through your data sheet, which you are going to complete by the end of this tutorial. So we are all set to start our presentation for today. Now, the biggest question which comes to our mind once you read PFT is that why, as a kinesiology student, I learned to know. The idea is that we want to talk about ventilation, which is the exchange of air between the atmosphere and our lungs, and it has two basic components: inspiration, taking the air in, and expiration, taking the air out or exhaling. And once we do exercise, this ventilation increases. And once this ventilation increases, we are going to have changes in our lung volumes and capacities. And we want to know through PFT that how our lungs are going to respond to exercise both normally and in case we are diseased, then how these values change. So we have a lot to learn as a kinesiology student about these pulmonary function tests because they have an important role to play while we are exercising. So let's start with the very basic definition. What is PFT? This is the classical definition written at the top, which says it's a wide variety of objective methods to assess lung function. So the basic idea is that we measure two big things. The first one is the volume or the amount of air and the speed or the rate at which this flow of air moves in or out. So the classical idea behind PFT is to measure the volume and how fast or slow this volume moves in and out of our lungs and how we exchange air with the atmosphere. Now, it's a good time to talk very briefly about how the air in our atmosphere moves inside the lungs. So this is a diagram which displays that at rest, when we are not breathing, before inspiration, there are three pressures which I want you to focus on. The first one is the atmospheric pressure, which is zero if we are not inhaling or exhaling. The second one is the intra-alveolar pressure. It is the pressure inside our lungs, inside the alveoli more specifically. And the third one is the intrapleural pressure, which is the pressure between the parietal pleura and the visceral pleura. So at rest, once we are not breathing, this is zero, this is also zero, and this is negative -5. So because both of them are zero, there is no air which is flowing because the pressure difference is zero. Now let's see what's going to happen once we inspire. Now during inspiration, our thoracic cavity expands, and once it expands, the volume increases, and as per the Poyle's law, volume is inversely proportional to pressure, which means that as the volume increases with the expansion of chest, the pressure decreases. So you can see this decrease in pressure. It has gone down from 0 to -1, and from -5 it is less than -5, and technically it's -8. So now here it's 0, here it's -1. So with a negative pressure in, air moves from high pressure to low pressure, and that's how we inspire. And the exact opposite set of things happen once we expire. Once our respiratory muscles go back to their original position, the pressure inside increases. In the atmosphere, it's again zero, so it's higher inside, lower outside, so the air is gonna move out. This is how our inspiration and expiration takes place. Okay. Now, let's have a few definitions which I want you to focus on before we dive deep into the volume and capacity stuff. So, the first one is hyperapnea. The term is self-explanatory. It is something which is increasing, and technically there is an increase in breathing. So, the ventilation increases. But the important point is that there is no change in the partial pressure of oxygen and carbon dioxide. So if we look into our blood gas analysis or the composition of blood gases of the gases in our blood, then that is going to remain same. It's only the respiratory rate which is increases and we are breathing more heavily. On the contrary, hyperventilation means that of course it's an increase in ventilation, but there is a significant change in the partial pressure of oxygen and carbon dioxide in our blood. So if the change in PaCO2 and O2 takes place, it's hyperventilation. If there is no change in both these parameters, then it's hyperapnea. Now, hypoxia means that there is reduced atmospheric oxygen. So if the oxygen in our atmosphere from which we are breathing in decreases, that is hypoxia. But if it happens inside our blood, that means it hypoxemia. So my idea was very simple, that these terms sound pretty familiar, but they have significant physiological differences as far as their meaning is concerned. So I want you to be familiar with them as we move ahead. Now, what is spirometry? As per the definition, as you can see on the screen, as the American Thoracic Society says, that it's a medical test that measures the volume of air an individual inhales or exhales as a function of time. So if you go back and think about the definition of PFT which we talked, it's these are the same two components. So that is the amount of or the volume of air, and if we take it in context of time or the flow or the rate, that is what spirometry measures. So spirometry is one of the methods of doing pulmonary function tests. Now in the next slide, I'm going to talk how we do those PFTs. I'm sorry, how we do the spirometry. So the patient assumes a certain position. You can see, you can do it by standing, you can do it by sitting. Here, he has to sit straight, so there is no pressure on the diaphragm, which impedes the breathing capacity. And then you put the nose clip on here, and then you put the mouthpiece inside your mouth and close your lips around the mouthpiece. So it's a specific position which you need to acquire so that there is no leakage of air from any of the angles of the mouth or side of the mouth, and you are directly inhaling and exhaling via this instrument. Now just concentrate. Now, once we take a few breaths normally, we will have this kind of reading on the spirogram. So all the peaks or the strokes which are up are the inspiration, or the downs are the expiration. And after doing these, taking a few breaths normally, we take a deep breath in, something like this, as much air you can inhale as you can, and then you will reach this peak, and then at this peak you try to exhale as hard, as fast and as long as you can. So you try to exhale as quickly and as fast as you can, and then you'll get this kind of graph. So my idea of putting this animation and explaining these steps is that if once you look at this diagram, you should be exactly sure that how this diagram is obtained while we are breathing, and how breathing is related to this particular graph. Now, the big discussion is coming up. We are going to talk about lung volume and capacities, and please put an emphasis on this term static. We are talking about static lung volume and capacities. We are not bothered about time. We are only bothered about volume, the first component of the PFD. So this is a big graph which you see on your screen. Don't get bogged down by the complicated things which are written. I will walk you through pretty easily, and I'm very sure that by the end of this graph, you will definitely able to interpret all those volumes and capacities. So the first one is the tidal volume. This part is the tidal volume. It's the volume of air which you breathe in or out. It's not and. So it can be this part or it has to be this part. So this is TV or this is TV. So once you inhale normally, once you exhale normally, this is the tidal volume and it's around 500 ml. Once you try to breathe in at the top of normal inspiration, so this is the top of normal inspiration, and the maximum amount of air which you can breathe from this point to this point is the inspiratory reserve volume, and the value is roughly 3000. And on again, once you try to exhale at the end of normal expiration, that's expiratory reserve volume. So beware that we are not talking from this point. We are talking from this point, end of expiration, maximum amount of air exhaled, top of inspiration, maximum amount of air inhaled is IRV, and the previous one was ERV. These are the three volumes. Now, if we talk about capacities, it means that we are combining volumes. So the first capacity, we just have to talk about the residual volume. So the residual volume is the volume which is left once you exhale as much as you can. And this whole is highlighted by this cream colored part, which says that this is the volume which will always there in the lungs once we exhale maximally. Now, as I've been talking before, if you add volumes, it will become capacity, and the first capacity is inspiratory. So if you add tidal volume and inspiratory reserve volume, you'll get inspiratory capacity. We don't have expiratory capacity. Just remember, there is no expiratory capacity. There is vital capacity for sure. So if you add inspiratory reserve volume, tidal volume, expiratory reserve volume, these three will constitute vital capacity. And if you add the residual volume to this vital capacity, we have our final capacity, which is the TLC, or the total lung capacity. So before we move ahead to the dynamic one, I quickly want to revise. We have the tidal volume, normal inspiration, expiration, inspiratory reserve volume, take a deep breath in as much as you can, expiratory reserve volume, exhale as hard as you can. Amount which is left is residual volume. If you add ERV, IRV, and TV, we will get the vital capacity, and if you add everything, you will get the total lung capacity. Now, this slide, you don't have to learn anything new. I just want to portray that whatever things we have talked, all those volumes and capacities, these are the different parts of the lungs where these volumes and capacities actually happen as far as the alveolar opening is concerned. Now, you can have maybe a 15, 20 or 30 seconds break, or you can come back after the lecture and fill this guided notes. So I want you to look at these arrows and fill from A to E about these static lung volumes and capacities. So you can look at it. If you can write in 30 seconds, you can, or at the end of the lecture, you can always look at it and write in your notes. All right, we are getting short of time, so I just want to move ahead. Sorry, you can always come back to it and fill it out. Now, let's move on to the dynamic lung volumes and capacities. The biggest difference is that the static, we are not taking the time component into account. With the dynamic one, we are bothered that how quickly these things are happening. So you can see that the graph remains the same. It's only the time which has came across on the x-axis. So we have only two things to learn: the FEV1, or the forced expiratory volume at the end of first second, and FVC, which is the forced vital capacity. So the first thing, one, it is the volume of air which you can exhale in the first second. So once you are trying to exhale as much as fast as you can, the volume of air which is exhaled during the first second is FEV1, and of course FVC is the volume of air which we breathe out forcibly after maximal inspiration. And the important part here, which you want, which or we all want to focus is this ratio, the FEV1 to FVC ratio. Sometimes it's called as FEV1 percentage. It is the ratio of FEV1 to FVC. And the important point here is that in healthy individuals, this ratio is somewhere more than 80%. Of course, different books have different ranges. Your manual says 75 to 80, some books says more than 80, but as long as it's more than 80, it's considered normal. And in disease conditions, this ratio dramatically decreases, and we'll come on to it once I'll discuss about the diseases. Now, you again have a 30 seconds break where I have put these values, and using this diagram, you can read a quick case history, and then keeping in mind about those parameters, you can fill in the values of FEV1, FVC, and then you can, this part of the question you can answer once we talk about the diseases. So you can put the value of FEV1, FVC from the graph, divide them, get the ratio, and then depending upon the ratio, you can comment whether this is an obstructive disease or the restrictive disease, which we'll discuss later. So you can have 15-20 seconds to look at it and decide about the things which we have already talked in context of dynamic lung volumes and capacities. All right, this part is not very important, but I just want you to include to enhance your knowledge about the pulmonary function test. This is the maximum volume of air which moved in a minute at rest. So MVV, or maximum voluntary ventilation, means that we measure the maximum volume of air in 1 minute. So we'll start the clock and we try to breathe like this as hard, as fast as I can, and measure the total volume of air. So the normal value is somewhere between 90 to 170 liters, somewhere in between. And this ratio VE by MVV, VE is the same thing during exercise, MVV is during rest. So this ratio, if it's more than 70%, it suggests that there is ventilatory limitations. So we can assess a person's ability to exercise or limited ability to exercise using this MVV. Now, FRC is another parameter which we haven't talked much in detail, but I want to talk it here. It is the amount of air which remains in the lung at the end of normal expiration. So if we are inspiring and expiring, now after expiring at rest, whatever volume is there in the lungs after normal expiration is functional residual capacity. And it has some really important clinical implications. That is why I want to talk about very briefly. The first one is it helps in the continuous exchange of gases. For example, if you are taking a dip in water or you are swimming, you have to hold your breath. But once you're holding your breath, you're not taking the air in, which means that the tissues of the body are not getting oxygen from the air. So it is the volume of air which is there in the lungs which provides oxygen, and there is a continuous exchange of gases going on between the lungs and the blood normally, even when we are holding our breath. And this also prevents the collapse of lungs if we are holding our breath, because some volume of air always there in the lungs. So there are two main functions. One is the breath holding, and the second one is the prevention of collapse. and you should be aware of FRC and its normal value, which gets really compromised in a lot of clinical diseases. Now, our last topic for today is that how PFT helps us in diagnosing pulmonary diseases. We will talk about obstructive diseases, the COPD, and the restrictive diseases. Now, I have highlighted the big differences between the two in this slide. And the first difference is that in obstructive diseases, we have problem while we are exhaling because our bronchi gets constricted because of the inflammatory exudates, and that is why once we take the air in normally, but we cannot exhale. On the contrary, in restrictive diseases, because of the fibrosis, scars, or tumors, the capacity of the lungs to expand um, heavily compromises and our chest cannot expand. So that has an important effect on the parameters which we have already talked. If you can see the flow rate, the FEV1 FVC ratio, which we have talked in our previous slide, heavily compromised or reduced in obstructive, but it has no effect on restrictive diseases. On the contrary, the static lung volumes and capacities, all those TV, IRV, etc., they remain constant here, but they get heavily reduced in restrictive. So keeping in mind the FEV1 and FVC, which is the dynamic and the static, we can always comment on the type of restrictive disease, and you can use it in your one of the guided notes examples while you are going through it again. The examples include bronchial asthma, exercise-induced asthma, bronchitis, and the examples of restrictive, I've already talked, all kinds of fibrosis, let's say scars, tumors, they will restrict the capacity of our lungs to expand. So keeping in mind the FEV1 and FVC ratio, we can always comment on the type of respiratory disease to some extent. And this is again a graph which shows that as long as the FEV1 and FEVC is normal, the ratio is 83%. But in obstructive, you can see a marked reduction in the expiration FEV1. So overall, the ratio decreased to 50%. Here you can see that these capacities have been compromised, but the ratio is normal. That's what I was talking in my previous slide. So you can use this diagram and our previous slide to just have an idea about how these volumes and capacities changes with a kind of lung diseases. Now, before moving on to this activity 14.1, I want to summarize what we have talked. We have started our discussion that why we need to know about PFT. Then we have quickly talked about the mechanics of respiration. Then we have talked about the technique of spirometry, the steps of spirometry, and we talked quite in a lot of detail about the static lung volume and capacities and the dynamic lung volumes and capacities. We focused on a couple of important ones, which includes MVV and FRC, and we ended our discussion with the how to use these dynamic lung volume and capacities, specifically the FEV1 upon FVC ratio to diagnose obstructive and restrictive diseases. So I hope that you'll get something out of this lecture of pulmonary function test. It will help you to solve your virtual lab assignment, as well as I can guide you to this lab activity 14.1. You can see that you have to fill in your basic details, the date, time, specifically concentrate on your gender and height and age, because these are the three things which you're going to use in solving the equations which are given below. So depending upon your gender or sex, which if it's male, use the bottom half. If you're a female, use the top half, and put your age in years and your height in centimeters. So if you get know your height in inches, just get it converted into centimeters. It's not written here, but you need to convert it into centimeters to put it in these equations. So depending upon your gender, age, and height, you are going to solve for the FVC, the FEV1, which we have already talked in detail, and the last three equations tells about the different equations to get the residual volume. which is the amount of air which is left in the lungs after we exhale. So, depending upon your gender, choose the top half or the bottom half of the page. Use your age, height, and gender, put into these equations, solve them, and of course, this can be graded. I hope you guys are doing great amidst this coronavirus pandemic, and we will continue our lecture sessions in the coming few weeks. And feel free to email me as much as you can if you have any confusion related to the assignment or whatever stuff we have talked. I'm more than happy to answer. Although it's a flurry of emails coming my way, so it may take a bit of a time for me to respond, but I'll surely respond pretty quickly. Thanks a lot for listening, and all the best for your assignments for this particular task. Hope to see you pretty soon. Thank you very much.